So, yeah, so welcome everyone who's here, who made it here today. And this is in fact the last colloquium talk of this academic year. And yeah, we will announce plans for the next year in time, hopefully still before the summer, but yeah, we need to discuss a bit in what format and which times and so. We'll see how that works out. But stay tuned. But for today, we have our final speaker for this year, Alison Liu, who has joined the department as an assistant professor already in 2019, but it still means she has spent more time working from home than working at the department, really. But yeah, we try to catch up on that soon. So as you may have guessed from the title, her research interests are in the area of design and analysis of online algorithms. We will hear more about that in a while. So she's not Dutch. She was born and raised in Taiwan. Then also studied there and has a dual degree from the National Tsinghua University of Taiwan and the University of Liverpool in the United Kingdom. And what I think a very interesting PhD trajectory to follow between those two locations. And then she went abroad more to Poland for doing a postdoc, and then from that on, that is what she decided to join Utrecht University. And her research at the moment here is still pursuing that general area. So it's on designing online and approximation algorithms for different application areas, for example, like resource allocation, network design, and all sorts of scheduling problems. And the talk she's going to give today, you will have seen the title, is about algorithms and uncertainty and how to make the best decisions. And with that, I just hand over to you, Alison.
Okay, thank you for the kind introduction. So today I'm going to talk about first the online computation and what is online algorithms. And based on the knowledge of online algorithms, I'm going to teach everybody how to take lifts. And in the end, I will briefly talk about our recent work on online algorithm for energy efficient scheduling problem. Right. So first, what is online computation? So online problem means that the input will not be given in the very beginning, but an online algorithm can only receive the problem input piece by piece. And once me as the online algorithm, I receive a piece of input, then I have to make the decision right away. And by right away, I don't mean that I should do it very quickly in a computational complexity way, but I mean I have to make decision not until I see the next input. And because of the uncertainty of the input, future input, whenever I'm making the decisions, I can only based on what I have seen so far. And once a decision is made, I cannot change it later. And more importantly, I have to guarantee that the performance of my algorithm is good enough. And usually the measurement of the performance of online algorithms is called competitive ratio. So what is competitive ratio? The formal definition is an online algorithm, if we are talking about a minimization problem, an online algorithm on is R competitive if for any input instance, the ratio between the online algorithm on this input instance to the optimal solution cost on this input instance will be less than or equal to R, where R is some number or variable that's greater than or equal to 1. And here by the optimal algorithm, we mean the algorithm which knows everything about the future and has unlimited computation power. So this is a very strong optimal solution. But on the other, in other words, we can say that an online algorithm is R competitive if for any other algorithm A, the cost occurred by the online algorithm to the cost occurred by the algorithm A on the same input I will always less than or equal to R. And here, we don't care if this algorithm is online or offline. So it can be either of them. So what does it mean? What does the competitive ratio mean? If you have some competitive ratio of your online algorithm, it means first you see some events here, and there can be several decisions you can make. You can choose one of these decisions, and each of these decisions will lead you to another scenario, and there will be another event happening. And you keep doing making decisions, and there are always new events coming, and you keep doing these until the end of the inputs. Now you, as the online algorithm, if you look at this black path, that is the decision-making path of your online algorithm. And finally, you have some costs incurred by all the decisions you made. And if you look at any path on this whole graph, for example, this orange one, it will lead you to another result and have another cost. And this is probably another decision-making path, and so on. So you have the competitive ratio of R, means that if you look at all the decisions you didn't make, all the paths you didn't take, it won't lead you to a much better for a R vector, better results. So having a competitive online algorithm is very good for no matter for your life or for your problem. So that is competitive ratio. Now we know what is online algorithm and what is competitive ratio. Now we're going to learn how to take the lift. Right. So imagine that you're on some ground floor and you want to go to the top floor, and you want to get to the floor as early as possible. There are several things you can do. You can, of course, take the stairs, and taking the stairs costs you 500 seconds. And you can also take the lifts. That will be faster. You only need 100 seconds to get to the floor. But now the uncertainty is you don't know when the lift will come. So any reasonable strategy will be you wait for a time period, and then if the lift is not coming, then you give up and start climbing the stairs. And because you want to get to the top floor as early as possible. So now how to choose these X, how to choose the time, the length of your waiting is the key of achieving your goal as good as possible. Here, this is an online scenario, so you cannot right. So you cannot Right. So you cannot decide to go to the floor, and then you cannot go to the floor, go to the stairs, but you saw that the lift is coming, and you turn back to the lift. That is not cool. We're not going to do that. So this is impossible. You cannot do this in this scenario. Okay. Right. So let's see some strategies. So here the x-axis is the time when the lift comes. So each point on the x-axis represent a scenario of the input, and the y-axis is the corresponding arriving time. So if we look at this strategy that always take the lift, then you can see that if the lift arrives at the very beginning, then you can arrive the top floor at the 100 second. Oh, right. Here, again, the stairs takes you 500 seconds, and the lift takes 100 seconds. So if you're taking the lifts and the leaves arrives at the 1000 second, then you will arrive the top 4 at the 1100 seconds. So that is the strategy that always take the lift. Or you can decide to take the stairs at the very beginning. So no matter when the lift comes, you will arrive the top 4 at the 500 second. And this is the optimal strategy. That if the lift comes before this 400 second, then the optimal strategy is to take the lifts. Otherwise, the optimal strategy is to take the stairs at the very beginning. And because optimal strategy knows everything about the future, so that's why it can decide to take the stairs at the beginning, even when it doesn't know, it haven't really seen what happened in the future. So here, this red line is the optimal strategy. And what is the online algorithm? This black line is an online algorithm or online strategy. And actually, this is the best online algorithm for this problem, for this setting. So it will wait until the 400th second and go to the stairs. So if the lift arrives before the 400th second, then the behavior or the result will be exactly the same with the optimal strategy. Otherwise, if the lift arrives after the 400th second, then we can arrive the top 4 at the 900th second, and that will be the same for all further scenarios. And this is the best deterministic online algorithm. So by deterministic online algorithm, we mean that you have any deterministic online algorithm will have a specific time waiting time. So after that waiting time, it will turn to the stairs. So any other deterministic online algorithms will either wait longer or wait shorter. But before that, let's look at the competitive ratio of these online algorithm. So here, these online algorithm, the competitive ratio will happen on this event when these online algorithm turn to the stairs. At that moment, the lift comes, and the competitive ratio will be 900 over 500, which is 1.8. And if we look at any other deterministic online algorithm, which is either waiting shorter or waiting longer, if we wait longer, then this yellow strategy will benefit from the events here. That is, if the lift arrives between 400 and 500 seconds. But then the worst case happens here. The competitive ratio of this yellow strategy will be this yellow interval over the red interval, and this will be greater than 1.8. Another possible deterministic online algorithm is this. We wait shorter than 400 seconds. Then we will perform better if the lift arrives after the 400th second. But now the worst case happens here. The competitive ratio will be this yellow interval over the red interval, and that will again greater than 1.8. Right. So far we have proved that this black line is the best deterministic online algorithm. So this is the best deterministic online algorithm. No other online deterministic algorithm can perform better than this one. But how about non-deterministic online algorithms? Actually, randomization helps. So one randomized algorithm is you flip a coin on the 222nd second, and if it is the head, then you take the stairs. Otherwise, you just follow the best deterministic online algorithm. And this will be the expectation of your arriving time. And the expected competitive ratio is 1.622. Why these work? This work because if eventually you have to take the stairs, but for some chances you may already taken the stairs, then you will get benefit from these. So at the moment you flip the coin, you actually create parallel universes, and you have different strategy in different universe. And one input instance cannot be the worst case input instance in every of the parallel universe. So that's why you can perform better. You can even flip the coin twice, once at 235 seconds and once at 326 seconds. Then you will get this expectation of arriving time, and the expected competitive ratio will become 1.598. That is a bit better than the competitive ratio of flipping the coin once, and much better than the case that you don't flip the coin. Right. So for everyone's convenience, I have some formulas here. So assume that the stairs takes you S second and the lift takes you L second. The best deterministic strategy is you wait until the S minus L second. Or if you're willing to flip a coin, the best timing for flipping the coin is at the square root of 5 times S squared plus 4 times L squared minus 8 times S times L minus S over 2 second. That is the best timing for flipping the coin once. If you are going to flip the coin twice, you can flip it at this time, this second or this second. But I guess this is not the most practical for everyone. So yeah, right. So we have done the lift or stairs problem. Now we're going deeper to another problem. That is an energy efficient scheduling problem, and we work on the online algorithm on this problem. So this is a joint work with Alison Liu and Prudence Wong. And this paper is motivated by the smart grid system. So in smart grid system, you have many tasks. Each of the tasks needs some power and has to be done within some time. And our goal is to finish all the tasks with as small as energy cost as possible. Yeah, right. So here is the formal definition. Right, this is the formal problem definition of the energy efficient scheduling problem. But we're going to look at the illustration right away. So first, we partition the time into unit length time slots. And each of the job or each of the tasks will look like this. There will be a set of feasible time slots, and the job can be assigned to the feasible time slots. And each of the jobs will look like a rectangle. The width of the rectangle is the time duration of this task, and the height of the rectangle is the power request. So for example, here we can assign the job to here or to here. And once we assign a job, the next job arrives and we will assign it to. So now how about the energy cost? First, we define the load on some time slot T. The load of the time slot T is the total height of all the jobs executed during the time slot t. So for example, the load on these time slots is the orange interval plus the green interval. And the energy cost at the time slots will be some function of the load. And in this paper, we consider that f is an arbitrary function as long as it is strictly increasing and convex. Our goal is to minimize the total cost over the time. So because of the convexity, it is better to not to put different jobs at the same time slot, but because of the restriction of the feasible time slots, we may not be able to do so all the times. And in this paper, we focus on the unit case, where each of the jobs has the unit size. That is, the width and the height are both units. So here is the combinatorial problem. So you can imagine that you get a bunch of squares one by one. Each of the squares has some restriction that it can be only placed at some spaces, some positions. And you get them one by one, and your goal is to put them as even as possible. So that is the combinatorial problem here. Right. So we're thinking about the greedy algorithm. So what does the greedy algorithm mean? The greedy algorithm is whenever a job is released, we just look at all its feasible time slots, and we find the one with the lowest load and put the job there. That is the greedy algorithm. For example, if we have first this job, because now all the time slots has the same load, they are all empty. So we can just pick one and put the job there. And when the next job comes, because all these gray time slots are empty, so we will choose one of them and put the job there. Now, the next job here comes. And because both of its feasible time slots have the same load, so we just pick one and put the job there. And the last job comes, we have nothing to choose. So we just assign the jobs. So here you can see the challenge of uncertainty. Because of the uncertainty, no matter how smart, how clever things you did before, the uncertain input can flip the world upside down and make everything you did before now looks very stupid. So that is why online algorithms are challenging. Right. So the top part is the greedy strategy, and the bottom part is the optimal schedule. Although greedy strategy is not optimal like the bottom one, but we do suspect that it is the best online algorithm. So in fact, in this paper, our main result is to show that the greedy algorithm is the best online strategy for this problem. How do we do that? So the following is the sketch of our proof. So first, we look at the universe of all possible input instances. So you can see that for each of the instance, there can be different cardinality among the different instances. Or there can be two instances with the same cardinality, but the jobs has actually the different feasible time slots. And it can even like they are the same set of jobs, but with different release order. So by the input instance, we mean the all possible input instances. We mean any set of jobs with any release order. Next, we classify the universe by the corresponding optimal schedule configuration. So this is a partition of this universe. If you look at this partition here, and if you look at any instance inside, for each of the instance, the optimal schedule will be 1 job and 2 jobs. And if you look at this class, each instances inside will have the optimal schedule, 1 job, 1 job, and 1 job. Right, so that is how we classify, how we partition the universe of all the possible input instances. So the first thing we did was we showed that among all the instances inside this class, there will be an instance, this blue one, which has the biggest greedy cost, which means if you run the greedy algorithm on each of the instance inside this class, this blue one will give you the highest cost. And the next thing is we show that for any online algorithm, A, let's say it is called A, there must be an input instance inside, again, inside this partition, that the cost incurred by algorithm A on this yellow instance will be at least the same or greater or even greater to the greedy cost of the blue one, the blue job instance. And because they are all in the same partition, so which means their optimal costs are the same. So we get this inequality. The ratio of the cost of A to the optimal cost on the yellow instance will be greater than or equal to the greedy cost to the optimal cost on the blue instance. That will be greater than or equal to any for any other instance, the greedy cost to the optimal cost. So that is our two main theorem. By these two main theorem, we can show the optimality of greedy algorithm. And here, please note that the second theorem works for any online algorithm. So we can have a yellow one here for the yellow online algorithm, and we can have a brown one for the brown online algorithm. Right. So now, if we look back to the whole universe, and there is a special input instance I star, where I star is the instance which decide the competitive ratio of the greedy algorithm. Within the class where I star belongs to, for any online algorithm, there must be an instance I prime that has the greater ratio between the the cost incurred by the online algorithm to the optimal cost of the same input to the greedy cost to the that is greater than or equal to the ratio from the greedy cost to the optimal cost on the I star instance. And by the definition of competitive ratio, we know that for this online algorithm A, its competitive ratio will be at least the yellow ratio. And so here it is greater than the greedy, the competitive ratio of the greedy algorithm. So that we prove that for any online algorithm, its competitive ratio will be at least the competitive ratio of the greedy algorithm. That means there is no other online algorithm can perform better than the greedy algorithm. And that concludes our work in this paper. So thank you for listening. I'm happy to answer the questions.
Thanks, Alison. for the presentation. And I mean, in the good tradition of the colloquium is now the point where you're allowed to unmute your microphone for a second and to give a round of applause that the speaker can actually hear. Yay! Always amazing that this works. Do we have questions? Just unmute and speak, or raise your hand before if you prefer. Maybe just start with a very, very superficial, lightweight question. But do you think of like this lift and stairs problem yourself when you stand in the ground of a building and need to go up? This is something that you can use to influence your own real life decisions, or is it rather not?
Right. So do you mean, do I flip coins when I'm waiting for the lift? Or if I'm applying
yeah. So if you need to decide like how you go up to the 5th floor or so, do you think about these things, or?
Yes, I'm always thinking about these things.
Yes. No, but yeah, I think we have some real questions. Pablo. Can't hear you yet? Yes. No. Yes.
It might be a very simple question, but forgive me, I'm not an expert in this sort of subject. But I was wondering, when you defined the best online strategy for the lift or stairs problem, you said that the best online algorithm was the one where you wait for 400 seconds and then you go to the stairs. And you said that the reason was that this is the one that minimizes the worst case competitive ratio.
Yes, the worst
right.
case. Yeah.
So, but then you said that an improvement to that is to flip a coin so that the expected worst case scenario can be lower.
Yes.
And my question is, if you, this is kind of a philosophical question, but if you're willing to go for expectation value, which is not always granted, you have to do the experiment multiple times to accomplish it.
Yeah.
Why do you define the best scenario as the one that minimizes the worst case competitive ratio and not the average competitive ratio?
I think that is the average of competitive ratio. So in different, you have different scenarios, and the solid line is the average performance.
I understand, but I think are you comparing then the average arriving time to the optimal strategy, offline optimal strategy?
Yes. So let me put it this way. So we will have a competitive ratio here, and another one is, I think, is 500 here. So we'll compare this one and this one, and see which is the worst. And actually, this is the best timing for flipping the coin once. So these two ratios are the same.
Yes, well, that's exactly what I'm not quite grasping. So alternatively, you could, and again, I'm not an expert in this, so forgive me, this is really stupid, but you could calculate the competitive ratio, or the ratio between the performance and the best possible performance at every point in time, and then compute the average of that. So basically take the integral of this and divide by the amount of time. And that would give you a kind of average distance between the expected performance and the optimal performance. But instead, you are taking the worst possible point to compute the competitive ratio. And the reason why this is, I mean, I'm okay with that. I'm okay with taking worst case scenario, but if you're taking worst case scenario, why is it okay to do an experiment that is kind of random and where you're computing sort of the expected worst case?
Yeah, I see your point. I think this is a different point of view on probably the same or very similar setting. That if you, like you said, you average on all the scenarios, that will be more like a stochastic input. So you have one algorithm on a random variable which indicates the arriving time of the leaves. So I think that is very similar, but a different point of view. So some people also do that. I think they call it stochastic model.
Okay, thank you.
Other questions? Otherwise, to follow up on this a bit, I think Pablo phrased it much more clearly, but I was wondering a similar thing also a bit with the energy efficient scheduling, like okay, what's the notion of best there, and also how results would change. I mean, you said like other groups are also comparing to an average or expected optimum rather than comparing to like like some worst case scenario or something. Could you say a bit more about that? Like what is like how do you choose what is the best and what to compare to?
Okay, so the best, I mean, here by the best we mean right. So here the best is there couldn't be another online algorithm that perform as good as greedy algorithm on its worst case.
Right.
So one worst case may not happen, may not be the worst case at the same time for the greedy algorithm and any other online algorithm. But if we look at the worst case performance of each online algorithms, then the greedy algorithm will perform the best, with the best performance at its worst case. So of course, this worst case may not be the worst case of the other online algorithm, and then the other online algorithm at on this instance may perform better than greedy. It is possible, but if we are talking about the worst case guarantee, then the greedy strategy will give you the best worst case guarantee.
Okay, I see. And how does the field work? So I think that's really like a theoretical result, right? I mean, you prove that this is like in case of worst case scenarios, but are there in this field also like, I don't know, practical like kind of challenges or competitions where people that try out their algorithms in practice and see how they perform on real cases against each other? Does something exist in that field as well, or not yet?
I don't know if there is any competition, but I know there are some papers or some works about they have some heuristic or they have some strategy, online strategy, and they show this is good by simulation or experiments.
Okay.
They will generate some inputs and apply the strategy on this input and see how it works.
Right. Yeah, I could imagine, especially for the scheduling, that there are probably like nice scenarios that one could develop as kind of like benchmarks and then ask other people to really try their algorithms on those, see what happens. Yeah. Okay, cool. Do we have other questions? Last chance for this academic year to get first-hand information from the speaker. It does not seem to be the case. I think people are longing for holiday. But anyway, Alison, thank you very much again for this presentation. And I invite everyone to give you another round of applause for this. Yay. And as I said, so this was the final session of the colloquium for this academic year. We will continue the colloquium after the summer break in some form. But yeah, we'll still need to discuss in which format at which time what the schedule will be, but you will certainly hear from us in time. If we don't see each other again, so have a good summer, hopefully with a bit of holiday break, well deserved and desperately needed by many of us. So take that as an opportunity that everyone is away and you can really do a holiday, and then really hope to see a lot of you again, and hopefully in real life when we are back to the university in September. Sounds far away, but time will fly. Thanks again, everyone. See you. Have a good rest of the day.